Okay, moving on from the method of differences now in this chapter on series, we're going to meet something really useful called the Maclaurin Series. And what the Maclaurin Series enables you to do is you might have a really complicated function that you might not be able to integrate, differentiate, and somehow if we can turn it into an infinite polynomial function, this will be much better to manipulate because of course we can then integrate, differentiate polynomials. So that's the important idea to start with, is let's assume we can somehow turn any function into a polynomial, but remember it's an infinite polynomial, so we'll have, coefficients a plus bx plus cx squared plus dx cubed plus ex to the 4, etc. And if I can somehow find out what these coefficients are, I can basically come up with a new polynomial to represent this function. Okay, so let's have a look what happens, for example, when x is 0. So let's have a look what happens. So we'll have p of 0. Well, if you put 0 into everything here, the only thing you're going to be left with is this constant term. So straight away, I know p of 0 is simply a. Hold that thought. Let's see what happens if I differentiate px. So let's call it p dash x. So that's going to disappear, isn't it? So this is going to be b. This comes down, so that's going to be 2cx. This is going to be 3 dx squared. This is going to come down. This is going to be 4e to the x cubed, etc. Something like that. And then let's see what happens at the first derivative when x equals 0. Well, if x equals 0, if I put 0 into all of this, anything including x will get cancelled out, and the only thing in fact left in this case is b. So hold that thought. Let's find the second derivative. So shall we do p dash dash x? Let's use that notation. Okay, so now this will start to disappear. Here I'll be left with 2c. Here this is going to be 3 times 2. Think of it as 3 times 2, but I'll just put 6 for now, 6dx, but remember it's come from 3 times 2. This is going to be 12, but remember it's come from 4 times 3. You'll start to sort of see a pattern soon. And let's see what happens if I find the second derivative when x is 0. I'm now going to get, well, this will cancel out, this will cancel out, all of these further terms will cancel. I'm just going to be left with 2c. Hold that thought. Let's do it perhaps one more time. Let's find the third derivative, p dash 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 x. Okay, so that will go, this will go to 6d here, and then bring that down. Remember that was 4 times 3 times 2, so that's 24ex, and of course this carries on infinitely really, doesn't it? And let's just obviously work out, we can soon work out the third derivative when x is 0. And all of these further terms will disappear because x is 0. So I'm just left with 6d. Think of that as 2 times 1. Think of that as 3 times 2 times 1. And of course, remember this came from 4 times 3 times 2 times 1. Okay, so going back to the original polynomial, I can say my original infinite polynomial then can be written as, well, a is p0. Add b, well, b was p dash naught x. C, or you can think of that as the second derivative of 0 divided by 2. So I've got p dash dash naught over 2, or 2 factorial, you could call that, couldn't you? 2 times 1. What have we got there? That was b, wasn't it? X squared. Sorry, that was c, wasn't it? I'm getting all muddled up now. And then d, well, you could think of d as p third derivative, p dash 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 naught divided by 6, or remember we were calling that 3 times 2 times 1. So I've now got here p dash 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 naught x cubed over 3 factorial, and you get the idea that this will carry on as we just increase in powers. We can sort of see the connection here, can't we? This is the derivative, that matches up to this number, that matches up to this power here. And of course, all the way along, we've been saying, well, my polynomial is actually equal to the more complex function. So p of naught is f of naught, p dash of naught is f dash of naught. So in fact, we write the Maclaurin series in terms of the original function fx equals f of naught plus f dash of naught x plus f second derivative dash dash of naught over 2 factorial x squared, and then we do exactly the same third derivative when x is naught over 3 factorial x cubed, etc. Okay, now so this is your Maclaurin series, and all functions can be written in this style as long as f of naught, f dash of naught, f dash dash of naught, etc. are defined. Yeah, so we must have a finite value for those. And you will see how useful this is. So as long as you're able to sort of, all I need to be able to do is differentiate the function. Yeah, so I could have a complicated function here that I might not be able to integrate. As long as I can differentiate, I can use my Maclaurin series, and you'll see how useful it will be shortly.